Solution for problem K. First of all, we have to convince ourselves that this problem is actually non-trivial because it seems at the first glance the same. They have sequences of the same length, so why shouldn't they have the same probability of appearing in a random experiment? The thing they have the same is not the probability of appearing. The thing that is the same for all patterns of the same length is the expected number of occurrences. This is from linearity of expectations. At each position in this random experiment, we have the same probability 1 divided by 3 to the length of the pattern that it occurs there. And the expected number of occurrences is simply the number of positions multiplied by this probability. So this is the same for all patterns. But the probability of actually occurring at least once may be different. For a simple example, consider these two sequences, either paper, 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 or rock, paper, scissors, and experiment in which we generate 4 random values. So there are exactly 5 different sequences of random values that contain p, 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 because it can be p, 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 and something, or something p, 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 but we are counting p, 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 p twice, so we have to subtract this. And for RPS, there are actually 6 different sequences, RPS here and anything there, and RPS here and anything there. So this one has a bigger probability of occurring at least once. And here we see what is going on. The pattern that could overlap itself could sometimes have multiple occurrences at the same time. And each time this happens, it decreases the number of different inputs, number of different results for which there is at least one occurrence, because we are taking the same expectation and dividing it. So a single case will produce multiple occurrences for this one. And it can be shown by doing the math more carefully that the actual probability is closely related to so-called periods of a string. So if we have a string, there are some shifts of the string, like this, that the overlapping part matches everywhere. So this length is called the period of a string, the length of the shift. And the shorter the period, the more of the overlap, and the more likely it is for the pattern to occur both here and here. And this probability decreases exponentially. So it can be shown that in order to solve this problem, what you need to do is take each pattern separately. For each of the patterns, compute the set of periods of this pattern. This can be done in linear time by using the Knuth-Morris spread algorithm. And then you can just take all of these patterns and order them according to this sequence of periods. The shorter the first period, the less likely it is to appear, the lower it should be in the rankings. Now, there are 2 common bugs in this problem. One of them is many teams, for their first submissions, are only considering the shortest period of a string and not all of them. This can matter especially if the shortest period is shifts by something like this, and then one of the strings can have also such a period and the other one doesn't. And in this case, those probabilities differ. And the other bug people are making is that the length of this actually matters. And when you are generating the list of periods, you have to stop at n. For example, if I give you the input where this length k is exactly equal to the length n, it doesn't matter what the periods are because all of the strings will be exactly equally likely. So you have to truncate this list of periods at the proper place. And that's it for problem K.